Dear students, welcome back. Earlier in my lecture, we saw the most commonly used symmetric encryption algorithm or block ciphers. A block cipher, it processes the plain text input in fixed sized blocks and produces a block of ciphertext of equal size for each plain text block. In this section, we will focus on the three most important symmetric block ciphers: the data encryption standard, then triple DES, and the advanced encryption standard. So, data encryption standard is the most widely used encryption scheme. It was issued in 1977 as Federal Information Processing Standard 46 by the National Bureau of Standards, now known as National Institute of Standards and Technology. Here, the algorithm itself is referred as Data Encryption Algorithm DEA. So let's see more details. So the plain text is a 64 bits in length and the key is 56 bits in length. So the DES structure is a minor variation of the Feastel network we saw earlier in the class lecture. There are 16 rounds of processing. From the original 56-bit key, 16 sub-keys are generated, one of which is used for each round. So, what's wrong here? The concerns about the strength of the DES algorithm, it falls into two categories. It concerns about the algorithm itself and the concerns about the use of 56-bit key. So the first concern about the algorithm, it refers to the possibility that the cryptanalysis is possible by exploiting the characteristics of the DES algorithm. But over the years, there have been numerous attempts to find and exploit the weakness, making DES the most studied encryption algorithm in existence. Despite numerous approaches, no one has actually succeeded, at least no one has announced it, in discovering a fatal weakness in DES. So that puts us the focus on the second concern, which is the key. So a more serious concern is the key length. With the length of 56 bits, you might think there are a lot of possible keys. In this case, it's a 2 to the power 56. But assuming that on average of the key space has to be searched, a single machine performing one DES encryption per microsecond would take more than like 1,000 years to break the cipher. But that's for one machine. However, the assumption of one encryption per microsecond is overly conservative. As I said, it's just one machine. So DES finally and definitely proved insecure in July 1998 when the electronic EFF, the Electronic Frontier Foundation, announced that they had broken a DES encryption using a special purpose DES cracker machine that was built. So that attack took less than 3 days. So they kind of EFF published a detailed description on the machine, and so which enabled others to build their own DES cracker. So with the hardware prices dropping off, basically making DES virtually like a worthless. So with current technology, speed of the commercial off-the-shelf processors, they threaten the security of DES. Yep. Recently, a paper from Seagate Technology, it suggests that the rate of 1 billion key combination per second is reasonable for today's multi-core computers. There is also another analysis suggests that the supercomputer technology can do 10 to the power of 13 encryptions is also reasonable. So technology is catching up pretty fast. That actually created the 3 DES algorithm. So because the original DES was kind of cracked up using the technology, 3 DES, which is called a triple DES, was created. This basically uses 3 keys and 3 executions of the DES algorithm. So the function follows like an encrypt, decrypt, encrypt sequence. So what happened here is, here with the 3 distinct keys, triple DES has an effective key length of 168 bits. Because DES has a key length of 56 bits, it's a triple DES, it's 168 bits, making it much more secure. Basically, the time takes to crack it, it's going to be a long time, years. So then what is wrong with this? Because the triple DES is using the underlying DES as the framework, and we know the original DES is slow. Even the triple DES algorithm is also slow. So that kind of pushed everybody into the third one, which is Advanced Encryption Standard, AES. So the principal drawback of the triple DES is that the algorithm is relatively sluggish. It's slow in the software version. So the original DEA was designed in mid-70s. Then the triple DES came in, and even though triple DES made it more secure, it is slow. Also, the secondary drawback with both the DES and the triple DES is both of them use a 64-bit block size. So for reasons of both efficiency and security, a large block size is desirable. So because of these drawbacks, triple DES was not considered a reasonable candidate for long-term use. It's kind of a replacement for the DES customers. They can switch to triple DES. It gives you that portability characteristics. As I showed you, the encryption, decryption, encryption. It allows the DES customers to port into triple DES, but it's not considered as a long-term, candidate. So as a replacement, NIST in 1997 they issued a call for a proposal for a new Advanced Encryption Standard, AES, which should have a security length better than or equal to triple DES, because triple DES was still considered highly secure. So they said it can match that or it could be more than that. And the important point was the new standard should significantly improve the efficiency. So that was a requirement. So in addition to these two requirements, NIST also specified that the new advanced encryption standard must be a symmetric block cipher with a block length of 128 bits. So making it much more secure. And they also said the key length should have the support for 128 or 192 or 256 bits. So this was the new standard which was proposed. In the first round of evaluation, like 15 proposed algorithms were accepted. Second round, they narrowed down to 5. Then they started doing the evaluation process. Then they finalized the final standard in 2001. I think finally that's how the AES algorithm was accepted as the final solution. And both the cryptographers are from Belgium. So what does it do? The AES, it uses a block length of 128 bits, just like the standard they requested, and a key length that can be 128, 192, or 256 bits. So in the description of this section, we assume a key length of 128 bits for rest of the slides, which seems to be right now the most commonly implemented, because even with 128 bits, it takes, you will see in the next slide, it takes many years to break it. So right now the vendors are not very much interested to roll out the 198 and 92 and 256 bit keys, but I'm sure as the technology catches up, this standard can grow. So you don't need to invest another standard. This can stay for quite a long time. Now let's see some comparison of these three. So this is kind of an average time. It basically shows how much time is required for a brute force attack for variable key sizes. If your key size is 56, how long it's going to take. If it's on 128, then your block size is different, so how long it's going to take. So this is kind of a comparison. So as can be seen, a single PC can break DES in about a year. If multiple PCs work in parallel, the time is drastically shortened, 1 hour. And today's supercomputers should be able to find a key in about like an hour. So again, key sizes of 128 bits or greater are effectively unbreakable using simply a brute force approach as of today. That's why you don't see many of the implementation of 192. Maybe it might be in the military, it might be still there, but in the regular commercial you don't see more of those implementations. So let's go to the next slides. Okay, so let's get back to there's a symmetric block cipher. That's what we saw. There's the three types: DES, triple DES, and AES. They process one block of data at a time. In the case of DES and triple DES, the block length is 64 bits, whereas the AES, the new one, the block length is 128 bits. So for longer amount of plain text, it's necessary to break the plain text into the block B block sizes, padding the last block if necessary. So to apply a block cipher in a variety of applications, 5 modes of operation have been defined by NIST. So the 5 modes are basically intended to cover virtually all of the possible applications of encryption for which a block cipher could be used. So these modes are intended for use with any symmetric block cipher, including triple DES and AES. So that kind of completes the symmetric block cipher types and how they work. The next slide we are going to see symmetric stream ciphers. So symmetric streams encryption algorithm, they are typically the stream cipher encrypts plain text 1 byte at a time. So they are often used for the speed and simplicity of implementation in hardware. It's easy just to do 1 byte at a time, They're also often used in applications where the plain text comes in quantities of unknowable length, like a secure wireless connection. You don't know how much you are going to get it. You are getting it, So that kind of situation where you don't know unknown variations of data, incoming data, those kind of situations, the stream ciphers make much sense to use it. Again, they are also often, they are used for the simplicity. So here, the most important symmetric stream cipher and the commonly used one is called RC4, reverse cipher 4. Here is the representation diagram of the stream cipher structure. As you can see in the structure, a key is input to pseudo-random bit generator that produces a stream of 8-bit numbers that are apparently random. The pseudo-random stream is unpredictable without knowledge of the input key and has an apparently random character. So the output of the generator, called a key stream, is combined 1 byte at a time with the plaintext stream using the bitwise exclusive OR operation. So here are the, this is a list of the important design considerations for a stream cipher. So the first one, the encryption sequence should have a large period, So a pseudo-random number generator uses a function that produces a deterministic stream of bits that eventually repeats. So the longer the period of repeat, the more difficult it will be to do cryptanalysis. Then the second one, the key stream should approximate the properties of a true random number stream as close as possible. For example, there should be an approximately equal number of ones and zeros if the key stream is treated as a stream of bytes. Then all of the 256 possible byte values should appear approximately equally often. So the more random appearing the key stream is, the more randomized the cipher text is, so making it the cryptanalysis more difficult. So in the next slide, let's look at the most commonly used stream cipher. RC4 algorithm. RC4 is a stream cipher designed in 1987 for RSA security. It's a variable key stream cipher with byte-oriented operations. The analysis shows that the period of the cipher is overwhelmingly likely to be greater than like 10,100. 8 to 16 machine operations are required per output byte, and the cipher can be expected to run very quickly in software. So where is it used? The RC4 is used in the secure socket layer, transportation layer security, SSL/TLS standard, which we will be seeing later in our course. It's also, RC4 is also used in the wired equivalent privacy web protocol, which you can see in every internet, and the newer Wi-Fi protected access protocol, WPA. So they all use RC4. So what makes RC4 stand out among the rest of the stream ciphers available in the market? So the RC4 algorithm is remarkably simple, and it's quite easy to explain. A variable length or key length, from 1 to 256 bytes is used to initialize as 256 byte state vector, and element S1 to it goes up to 255. So there are a lot of technologies which is pretty easily understood. So number of research papers have been published analyzing methods of attacking RC4, so this is also well studied. So none of these approaches have proved any vulnerability against RC4 with a reasonable key length, such as 128 bits. So it has been well studied, it's well understood, well studied, and kind of well tested as well. So there are certain problems that have been reported so far, but it's still, RC4 is widely used, and it's the top of the list on for the available list of stream ciphers as of today. Okay, so that completes our lecture 2. In the lecture 3, we will be seeing, that's also going to be the last lecture, we will be seeing about the random numbers, then other topics related with the symmetric encryption. Thank you.